Here is Denis, colleague of my colleague. We work for Positive Technologies and we develop PC application firewalls. And today we are going to discuss WOF.js, which is one of our systems modules which works in the user's browser being responsible for application protection on the client side. This is the agenda or presentation. First, I will describe WOF.js, its capabilities, then I'll dwell upon the tools that we used for development. Then we'll proceed to the description of the application protection methods with the use of WOF.js, and then we'll say a few words about our roadmap. But first, WOF.js is believed that WOF is purely server application, purely server solution designed to protect with web applications only having HTTP requests and responses. But in fact, app protection is not confined to the server side. It is possible to insert JavaScripts to the browser to increase the scope, to look into users' browsers in order to see the environment and check various types of attacks in the context of the user's browser. Therefore, we are talking about CSRF attacks, about reverse clickjacking, and most importantly, it is about DOM XSS attacks that are not possible on the server side. We developed WOF.js using the JavaScript proper for assembly systems. We use Grunt. Casper.js was also used. We fully emulated the request-response cycle in the browser. One of the most critical parts is DOM Purify for HTML filtering. 53 is supportive of this project. Supporting it as part of the open source initiative. We are going to share with you our experience of using DOM Purify for non-standard tasks. Our task is as follows: not knowing anything about the application and its context, we need to guess and identify what we need to find on the client side rather than the server side. We will describe the advantages and disadvantages of DOM Purify, what it can do and what it cannot. We also use Acorn JavaScript parser to detect DOM XSS. We also use Sprima, another script parser, to generate the script itself, the configs. And we also use JSCS and DSLint to check our code, to check the style. Now let's proceed to the main part of our presentation, which is application protection with WOF.js. And we will start from the protection of CSRF. In many ways, it is about inserting a token in static forms, allowing to eliminate the possibility to send a request on behalf of the user from a third-party website through a submit application. With WOF.js, we can insert CSRF tokens dynamically. In other words, using advanced browser technologies, we can track the dynamic form creation with object mutation observer. We can not only insert it in static forms, but also in dynamic forms. It allows us to avoid false positive results that may be related to the blocking requests to REST APIs, which mostly use JSON and XML formats. We only look at those content types that can be used when sending HTML forms. I'm speaking about multi-part and some others. WAV.js also inserts a header, which is done by rewriting the XML HTTP request object, which is responsible for the requests with the use of Windows XML prototype. In older versions, we redistribute proper methods of popular libraries such as jQuery and others. Now let's proceed to the protection against reverse clickjacking, which is a pretty new type of attack, and we should distinguish two works here. Two studies by Pavel Toporkov and Ben Hayek. Despite the fact that two different terms are used here, it is virtually the same. The main characteristic of the presence of vulnerability is the control by the attacker of JSONP endpoint functions. In other words, the attacker can insert his or her function, and normally JSONP endpoint does not have validation based on wide list to validate functions and features. It allows to implement and execute any function in the context of the target application. In his study, Pavel examined the attack on one of Google's services which allowed to execute XSS through reverse clickjacking. In the second study, a more complex method is used, which is based on the usage of opener property of the Windows object, which examines the document that opened the link. The protection here is plain and simple. Everything that we need to do is checking all the incoming data in our location search or location hash to find out if the window object has this property and make sure if this property is a function. It can look like this. We check that there is a property in the window object. We can also use our DOM Purify blacklist. We can also examine the user environment for the browser features and characteristics, which will help us to identify bots which can render pages. In a simple scenario, such bots can be detected by using agents, but should they be masked, we need to look into DOM to look for specific DOM.js features and properties which allow us to detect Selenium. We can even scan the user's environment, his open ports, for some specific names to find out, for example, that there is a certain scanner working in the environment, and we will get an alert. saying that this user may be undesired on our website, and we can block him with the usage of the proper client script. The majority of the techniques that we use to detect malware is described in the book, The Browser Hacker's Handbook. Dennis and I highly recommend it for reading. How does Phantom JS bot look like? We check it for specific properties. That's what we do on the server side. There are plenty of methods for Phantom JS bot detection. In shape security, we recommend that you use this link and visit this resource. Beef is framework for XSS exploitation. We can also detect Beef cookies inserted in the user's browser. Beef supports two modes of operation. One is concealed, and the other one is open. In the second case, in the latter case, it's enough to check Beef properties of the window object. In the former, despite their attempts to mask those properties, we still can use methods that are only typical of Beef. On this slide, you can see how Beef itself detects burp. We use burp and proxy paths here. Burp renders a script that allows to set up the proxy automatically. If in the user's browser this name is resolved, we can say that there is burp working on it, and that the browser is operating, is running via a burp port. Instead of using proxy pack, we are using an icon. The advantage is in that we're using dynamic image object that allows to load our icon, which is in fact an image. And with our onload handler, we can detect the presence of burp in the user's environment. Similarly, we detect Fiddler. The only difference is that it does not have an icon, but there is a certificate on the 4.8 port. We can detect this file based on time delay. If the port is closed, the delay will be bigger. Should it be open, the search the detection will be instantaneous. And now we're proceeding to the main part of our presentation, which is about DOM XSS injection detection and protection against it. And I'm passing it over to my colleague. Well, our main objective, the main objective for any web application firewall is detecting such attacks. Let's identify the environment in which our tool is going to operate in order to understand which methods may be required. What do we have? We want to implement it on the client side to be able to use DOM this XSS. If we look at all the tools that are used to identify DOM-based XSS, we will see that the classical method is about identifying sources and potentially dangerous functions, which is syncme. And then we use, if it's possible, to implement flows between sources and methods. This approach is pretty difficult if we are using firewalls and we cannot rely upon it. However, we can use this approach if there is integration with an application inspector in the future. One of the most important points here is that we are not aware of the context in which our data may be found. If source code analyzers know the function, at least they can see it, they can build an AST for this code. We cannot do it. We don't have anything of this. We can only see our parameter values and engage in guesswork to find out where it can be found, URL or HTML or JavaScript and so on and so forth. Next, we cannot wait for full loading. Just one technical detail. Our component should work out in the first place, because if original application scripts are executed first, they can be executed at DOM XSS. Later they will be discovered, but there'll be no point in it. A lot of sources, a lot of resources were studied while working on this task. Here you can see three very different approaches. An attack can be discovered on the server side with the usage of class components. DOM-based XSS can be identified through syntax analysis, but it will require external browser modification. And there is also a study by Mario Heidrich, who writes against prevention of XSS attacks. Okay, how can XSS be discovered? Two most important points. We have to know where to search. For this, we need to know how to analyze data that can be controlled by the violator. Some of those data types are presented here, not all of them. If you need the full list, you'll find it in DOM XSS handbook. They are location, window name, various open storages, global storages, and so forth. And we also have to know the properties of the attack. The main property of an XSS attack is possible changes of parsing in a certain context, which can be HTML or DOM or JavaScript. The main attribute is that one of the trees of such parsing will be modified after an attack. Here you can see some XSS examples for different contexts, such as HTML, JavaScript attribute, or URL. What kind of strategy can be used for a protection? We need to get data somehow, analyze those data, and then make sure or find out if they contain dangerous HTML. If the answer is yes, we should ban them. Otherwise, we should check if they contain any dangerous JavaScript elements. If there are no such dangerous elements, the data are valid. And the key word here is dangerous. What does it mean? It is determined by our security policy. It can be a call to some JavaScript function, or an onload, or on-air attribute, or something like that. If we add our grammars to the four contexts, if we see such a vector anywhere, based on which grammars can we understand that it is XSS? In the first place, it is HTML, or it can be JavaScript. We can look into our JavaScript grammar. With JavaScript, we can also analyze our grammar. For URLs, we can look for pseudo protocols or JavaScripts called through those pseudo protocols. Since our first step is trying to identify a dangerous HTML, we immediately feel an urge to use an efficient tool. And such tool can be our DOM Purify library, which is developed and supported by Cure 53 team and some other projects. What is DOM Purify? DOM Purify is a library for developers. It has nothing to do with any WAF. It's not a tool to detect DOM-based XSS. It is a library that is designed to work with HTML codes and so forth. One of its features is that it is a pinpoint mechanism. It's not a heuristic mechanism. Since we work with WAF, working with application screens, very often we are unable to ensure accuracy, and this is an accurate tool. It will be working 100% in accordance with your policies. It is a tool for developers, and it supports cook mechanisms. You can write different modules, redefine the logic of HTML analysis and use it in your projects. What can DOM Purify do? It can prevent XSS attacks. At the input we have a dirty line, which is exactly the HTML that will be generated by the user. For instance, if you have a built-in editor in your application where user can generate it, well, this is exactly what it's designed for. The policy is defined with a lot of settings, like private tags, like in our first example, and then DOM Purify is used, and of this all HTML, well, we see that only these 9 are allowed. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we can see here various examples of using DOM Purify for various attribute resolution and so on. Another important point. It allows to prevent DOM clobbering, which is an attack where an attacker can send to the application DOM elements such as, or can send to the function field names and so forth. In this case, DOM Purify will be blocking them. Another important point is preventing attacks against HTML structure, which is a very interesting attack. Zalewski described it perfectly well. If you follow the second link, you will find very interesting information there, and file descriptors, well, and examples of how it can be used in Twitter. The following logic is implemented in DOM Purify. DOM Purify is based on the client, and it uses DOM parser. In this case, if the line only contains the opening tag with no closing tag, it will be empty, thus preventing this type of attack. We would like to use DOM Purify in the following way. We would love to be able to take all the incoming data, to send them to DOM Purify, and should DOM Purify say that the data are invalid, we would ban them, and all the way around. These are some of the features. of DOM Purify that are hard to use. In the first place, the order of attributes is changed. There can be additional closing tags. There can be double if we see such a line on the input, on the output, attributes will be different. It means that we are in no position to use DOM Purify directly. Well, in this case, we come up with absolutely different data. We can compare those data, but we don't know how to do that. Moreover, for data analysis, we require normalization. What shall we do? Should we have single quotation marks instead of double quotation marks and so forth? Another interesting point. If there is now opening tag, DOM Purify is not going to do anything. It means that all the XSS vectors coming to the JSSX context will not be identified by DOM Purify. They cannot be trapped, not because DOM Purify is a bad tool. It is because it's designed for an absolutely different type of task, and we want to use it on the client side. Okay, here is an example of DOM Purify failure. Should we deal with hypothetical application? There are data that come as a result of an injection. The data are inserted in the script context, and DOM Purify fails. Similarly, if data find themselves in an attribute, or URL, here you can see the example of a reverse clickjacking sum attack. And again, in this situation, if there is no opening tag, DOM Purify is going to fail. How can we adapt DOM Purify for our tasks? If we have at the entrance certain X line, we calculate the result of DOM Purify application to this line, and then we compare the lines with tag shift accuracy, for example, single or double quotation mark. If the lines fail to coincide, we believe that the entered vector is HTML, and secondly, it fails to comply with our policies, and we do not return a sanitized DOM Purify vector. Instead of that, we return a preset value.
Or it can be suffixed as string, just like in other web applications. So the function as it is shown on the screen. So this is an example using DOM Purify for data sanitation. In this way, as part of our strategy, we implemented the first stage. The data received go to the input of DOM Purify, get processed, and then if the data contains nothing dangerous from the DOM Purify point of view, we have to analyze them for dangerous objects of JavaScript. So what's the next task? We have a string that can get into the JavaScript context. So in actual fact, it's a JavaScript language code, possibly. And we need to understand, if it is a JavaScript language code, or it's something similar to JavaScript code, whether it contains any malicious functions. So what are the approaches to solve this problem in principle? So this is basically a problem of detecting an injection within a web application firewall. So the first thing that we can use is regular expressions, which are used in many cases. The second approach is lexicography signature-based. It's in the libinjection library. When you do lexical analysis, then you build a sequence of tokens in some way. In some way, you get a string of fixed length, 4 or 5, limited length, 4 or 5 tokens, and then this sequence is compared with the signatures of attacks. So this is the second approach. And finally, quite recently, maybe 6 months ago, firewall technologies have started to address the syntax analyzer-based approach. At 0 nights, it was proposed that an approach be used based on parser generators, kind of a universal approach, which is available in the libdetection library at GitHub. Doing this, it's important to develop the grammar. In our case, we needed to comply with the NCMI spec to build such grammar, build it on some parser generator, and to use it. But we decided to go a different way. We decided to use existing parsers, JavaScript parsers, or written in JavaScript, adapting them for our particular problem. So the approach that we're offering is quite universal and can be used for any languages. It's important that we need a high-quality parser. So what's the idea of this approach? We must allow data only in the case where the JavaScript does not contain any dangerous functions. So there's some string. We need to build a decomposition tree, and then look for some dangerous or malicious constructs there. If such constructs are found, we need to ban these data, and if they're not, then we need to allow this data. Of course, this is a heuristic approach. It's not a stringent method like DOM purified. There can be false positives. But nevertheless, the approach, the substantial advantage of this approach is that the difficult task of parsing of such language as JavaScript has already been solved, and it can also be solved for other languages. This way, we can use this approach to protect structures in other languages. This concept is illustrated on the following example. So the input data gets into the script context. Everything that the user has entered will be executed directly. If they enter 4 ones, then the ASC tree for this string will contain such nodes: program, expression, statement, and literal. Literal will have the value of 4 ones. And as a result, we'll get this code. If we enter this value, which for the right context will allow us executing the alert1 command, this line, if we pass it, will contain a dangerous construct, call expression. If we see call expression, then we need to ban it. So this is the approach that was implemented for browsers in our second research project. And it used the following criteria. These tainted data must generate only trees containing literal nodes and no other kinds of nodes. Well, based on the approach I proposed, what are the requirements? These are the minimum requirements. The parser should be is written on JavaScript and works in a web browser. That's why it's high performance. The primary analysis showed that the two candidates are available, Acorn and Esprima, two parsers. And now let's speak about what needs to be done for that. What stages do we get as part of this problem? Let me remind you of the problem. At the input, we get some string, and we need to detect banned JavaScript constructs within it. So what do we need to do? We first have to understand which of the contexts it can get into. There may be different contexts. It may get into absolutely different parts of code within this JavaScript. So we need to understand where it can get. Then we need to build the tree, find the malicious code there. And then, if we haven't found anything, maybe we should continue the search in some way to double check if we haven't made a mistake choosing the context. Depending on how we implement each phase, and we can implement each phase in different ways because the whole approach is heuristic. There are lots of heuristics emerging at all the phases because we don't know where the data gets and what kind of data we're talking about. We can, well, a lot of search methods can be proposed. Like these, for instance. And let's now discuss how all these methods work so that you can understand when they're applicable and when they're not, and so on and so forth. So what's the context computation? So we get an alert 1 line at the input. If we pass alert 1, we'll get call expression node. It is banned. But if alert 1 comes in double quotes, then from the JavaScript parser's point of view, it's not going to be executable code. It'll just be a string containing alert 1. But depending where this alert 1 gets, it can be malicious code or it may not be one. And we need to be able to process both situations. So therefore, how in the simplest case this problem can be solved? A set of search templates is built. Let's var a equals this. So we will need to substitute these strings into the string with the definition of the var variable, and do the parsing. If we had a string, or the other one, we're going to get a banned node call expression. If we had the first option, alert 1, they will get in the same context, it will be just a line. The second option is when we're trying to compute the context. How can it be done? We can count the number of tokens. Well, as known, in JavaScript, the data can be just data, and there are two types of string literals with single and double quotes. We can just compute the number of tokens for just data and concatenate it from the string with one quote and double quotes, and compute how many and count the tokens. Where the tokens are, there are more tokens. That's the context where the bad guy tried to get. The second problem is the tree building. We believe we build a tree from the ready-made parsers. It contains excessive information that allows us making a conclusion about the effect of injection. After we've built the tree, we need to find potentially dangerous constructs there. It can be done just either through a list, indicating a list, in our case, call expression, or we can use some request or call language, or we can define some logic and then to analyze the sequence of these nodes and so on and so forth. In these examples, for the sake of simplicity, we'll believe that the security policy defines banned nodes as call expression type of nodes. An example of how in the simplest case, we can just look up for the existence of banned nodes. So we run through this tree. If we go from the call expression and from its root, we find call expression. It all looks great, but we immediately get a problem, which is shown here. What to do if the tree cannot be built? Imagine we're getting a line like this at the output, and it's at the input, and it's obvious that it's very easy to build a context where this data is going to be very absolutely valid, but we don't know the context. If we compute the context for this line, the parser will not work with it because, from its point of view, this construct is not going to be valid, and it's not going to build any tree, and therefore there will be nothing for us to analyze. In this case, what we need is to proceed from the information that the parser brings back to us, if it does bring it back, to try and determine the remainder, the part of the string where we have valid JavaScript. Or the second option, which looks more right, we need to stop building the tree just as soon as we find banned nodes. So, and only Acon has this capability. The Acon parser is modular, and it allows the developer to write those modules that are going to be executed when building the tree. So this is exactly what we need. We have a string. It doesn't matter what it's going to have at the end, what kind of trailer, which part of the context. We do the parsing, and if the beginning of the string is valid, we can just add some special module, which will do the same. If it finds banned nodes, it will immediately send a message, and we sanitize the data. So for the present, for the time being, this capability is only available in the Acon parser. So it's very good to use it in this context. So therefore, we have a set of requirements for an ideal parser, based on which we have developed our experimental protection mechanism. The same three things: being able to change the methods of tree building, and what's also important, that it would be very good if this parser should also be able to operate in the error-tolerant mode. So we now know what kind of methods we have, and let's take a look at how they work. So the first one is based on preset templates. Where do we get these templates? From some typical places where the developer puts user data. For instance, these signs show the place of data injection. So if we get this input, we put the string into each context and do the parsing of each such string. And in this case, in the third case, we are going to have the tree built. So it's in the third case that we detect an injection. Search with reconstruction. So we get a line at the input. We normalize the data by using the applicable context. So we've added a double quote, and we've seen that it's in this case that we'll have the largest number of tokens. And we'll start doing the parsing. The parsing can't execute because an error is generated at the second symbol. So what do? We eliminate this part of the string, do the parsing again. Now, at the end, each last symbol will bring about an error. Then we start deleting these symbols based on the information that the parser generates for us. As a result, we arrive at this kind of expression where we build the pass-3. If we find a band node there, it means that we have detected an injection. That's the second option. The method that's whose idea is the closest to the one that we're using. We have the line S and the context CTX. Let's believe that the context has been computed by us and we know where it gets. So what do? We build old tokens using lexical analysis. We build the pass-3. And if in this pass-3 there are bad tokens, then it's an injection. If not, then we delete the token on the left and do the passing. What do we get thus? The band nodes have been determined and the string has been determined. So if we apply the context computation algorithm, the context will give us a double quote. So we do the analysis. The following sequence of tokens is built. We concatenate data with the proposed context and do the passing again. And again, an error is generated. So we go from the left and delete the token. Here we see the true pass-3 generated, and we can do the analysis. Please note that the trailer here is still syntactically invalid at the end. But because we have the acorn parser, which is modular, we can stop the parsing at the phase when we've already seen a band node. So therefore, we don't need to run to the end of this string. So this is the kind of pass-3 that's going to be built for this example. In this particular case, we'll see that we have a band node with call expression, a fragment of code that illustrates this idea. So what does this approach allow to identify? We've chosen vectors that were reported in triple recently with different XSS. And by the way, this XSS is not only DOM-based, but also server-based XSS. In certain cases, we see overlaps, and we can identify server-based XSS. But on the whole, this approach cannot be used for this, because the entire normalization that's typical of server-based applications cannot be executed in our case, because we have worked in the browser and the principles of normalization are absolutely different. There were a lot of client-side to play template execution vectors in Uber, Podswiga. There are very interesting Q53 mini challenger vectors identified. Reflected file download are identified in this case as JavaScript code, so it's quite natural it's been detected. ES6 is detected standard, and it's enough for us to switch on the support for the standard in the parser. So what is not supported? It's a very curious example, which, well, several years ago, there was a famous prompt-to-mult challenge for XSS run, and there were hidden levels. So this is the most difficult one, the fourth, hidden level 4. Please take a note of this object. It's syntactically invalid in terms of parser. But this vector managed to work in some versions of Chrome. Why? Because Chrome parsers were operating in the fault-tolerant mode. As a result, this method executed successfully and could even be used in such a construct. Thus, it is very beneficial and necessary to extend the scope in identifying XSS to have an error-tolerant parser. Of course, the number of false positives grows here, but at the same time, such vectors can be identified as this one. If in the previous case it couldn't be identified in principle because our parser runs without fault tolerance, whereas the Chrome parser does work for in this mode, which means that the attack will succeed in one case and fail in the other. So what do we get as a result? We get such a flow chart for the protection mechanism using DOM purify, and then a block of code which can be used IS-US parse. If the data in both cases don't pass, then we allow them. How do we minimize false positives? Perhaps it's a natural question for you to ask. How many false positives do we get? No doubt, there are false positives. They happen in any firewall applications. And how do we fight them, control them? The first mechanism that we have is the extended configuration. The configuration allows us identifying the class of the source of analysis, like window type of object and some other things. Then you can send context for sources and several parameters. For instance, you can identify that parameters with name A needs to be processed in one context, and with B in HTML context, for instance. Also, you can set for instance, valid constructions of A.B, where A.B is an extension. Well, basically, B is an extension of a file named A. You can implement checks in the Acorn modules. So preset profiles for security. And finally, testing. A lot of type data, typical data, is used, or standard data is used, which are used in popular applications, in local storage, in messages, in cookies, and so on and so forth. Because in modern applications, anything can be passed. JSON in cookies, JSON in local storage. It can be stored there, or some data arrays, anything. Well, basically, we don't really have a lot to say left, just drawing the results. Generally, we believe that the XS theme is not for the server side. On the server side, XSS can be detected, of course, but just out of curiosity, because it's not going to protect the users in any way. Most servers can only see the HTML context, and you need to do this protection on the browser side. I'd like to say that DOM Purify should be implemented as a standard library, as a standard component of any browser. And it's very strange that up until now, people have not been concerned about that, and the standard doesn't even have any initiatives to this effect. And looking forward, we are planning to implement the signing of a AJAX request on the client side. We're also going to get protected from phishing attacks, in particular from the tab snapping attack via the opener by adding a no referer for references. And we are going to warn users about self-access, just like what they do in Facebook. So that's basically it. Thank you. Questions? Can you please tell me, in practice, how do you instrument the DOM to check, like a post message comes to you. Do you check all the incoming messages, all cookies, all changes in local storage? It looks like a lot of data on the client side, of course. They said you have run the beef check, the bird check for each case, plus an additional check for DOM purify, and then after that you've even run your own logic. It's like a small client-side DOS. So privately, do you privately check some special events on a specific page, or do you check the entire page? Well, technically, we insert our script right into the tag hat, right, so that it should run the first. I don't agree with your saying that it's like DDoS, because all these checks are quite lightweight. It can be switched on and switched off. The injection object is quite fast. Well, there may be a dozen sources or like that, but it all runs pretty fast. As to the post message thing, the specificity here is that we set our callback for the message type event, but in this case we can't protect the user because our browsers don't allow avoiding the message being sent forward. Even if we do written false in our callback, this message will anyway go to the destination. Here we can only document the fact of attack, but can't avoid it. How do you insert in the browser? Do you have some centralized manager? It's all done as a part of the PT application firewall. It's all enabled by just one tick. There's a configuration which you can set up and either enable or disable certain checks. So, that's your WAF. Yes, that's our WAF. Should it be installed in some modes? Reverse proxy? Yes, I'm only talking about reverse proxy. In the passive mode, we can't change the response, so it's not going to be effective. So it comes in with the traffic. Yes, it gets dynamically inserted in the traffic. Yes, thank you. Unfortunately, our time is up. Thanks, everyone.